Okay, this video is going over topic 1.6, photoelectron spectroscopy, which the point of this topic is to explain the relationship between the photoelectron spectrum of an atom or ion and the electron configuration of the species and the interactions between the electrons and the nucleus. Okay, so there's a lot going on, but basically what we're going to do is we're going to look at a spectrum and we're going to be able to analyze that spectrum to determine the electron configuration. And then we can use that to then draw some conclusions about the behavior of the atom. So let's look at what this spectrum looks like. Okay, so photoelectron spectroscopy is also referred to as PES. So what happened in this type of spectroscopy are high energy photons are directed at a sample. Okay, so our example PES here is one for chlorine. So those photons hit the atoms and the electrons are ejected. So what gets measured by the sensor is the kinetic energy of the ejected electrons. So that's what is being measured. So you can imagine that electrons that are in the same energy level are going to be ejected with the same amount of energy. Makes sense, right? Same energy level, same amount of energy. Okay, so that's how we can draw conclusions between the energy levels and how much energy the ejected electrons have. Now, if you look at the spectrum on the y-axis, it says relative number of electrons. So what we're looking at are the relative sizes of the peaks. So this is helpful to look at the whole spectrum to then be able to kind of break it down, because you're not going to get actual numbers on the sides. What you're getting are relative numbers. But we can use those to then draw some conclusions about the actual numbers that are there. So let's talk about how we can interpret this. So higher binding energy, lower energy levels. Okay, so Coulomb's law tells us that the electrons that are closer to the nucleus are going to be held a lot more tightly because it's lower distance, greater force. And that attraction between the protons and the nucleus is going to hold on tightly to those electrons. So your higher energy is going to be your inner energy levels. Okay, so if we look at this spectrum here, okay, so if we're looking at our x-axis, so that's the energy. So I know that over here where my higher energy is, this is essentially my nucleus. Okay, so as I get farther away from my nucleus, my energy starts to go down. Okay, so I could guess that I have one chunk of electrons here, I have a chunk of electrons here, and I have a chunk of electrons here. Okay, so that tells me that it probably, most likely, has 3 energy levels. Okay, now this particular spectra, we know that this is for chlorine. Chlorine does in fact have electrons in 3 energy levels. Now, the next part of the interpretation is that the height of the peaks is proportional to the number of electrons. Okay, so I know if I have 3 energy levels, they're obviously going to be completely full from the inside out. My first energy level is just the 1s. So I know that if this one, since this one has to be completely full, this height is equal to 2 electrons. So I know that here in my first energy level, that would be a 1s2. So I'm starting to use this to build my electron configuration. So there's my 1s2. Okay, so I'm going to move up into my next energy level. So now we're in the 2, so we've got 1s2, so now we're in 2. I'd obviously have s first. This, there's 2 parts to looking at this one. First, you could say, well, it's the same relative height as the first one, therefore it must mean it also has 2 electrons. You could also acknowledge that for there to be electrons in more energy levels, it has to be full. Okay, so we've got 1s2, this would be 2s2. We know with our electron configuration after 2s2 comes 2p. This peak is roughly 3 times, should be actually exactly 3 times the height of this first peak. So if this first peak represents 2 electrons, this one would be 2, 4, 6 electrons. Also, if you know that you've got electrons in later energy levels, this one obviously has to be full. So we've got 1s2, 2s2, 2p6. My next chunk, my lower energy, is my highest. My lowest energy electrons are going to be in my highest energy level. So again, I'm in energy level 3 now. So now I know I'm going to start with 3s2. Also conveniently enough, this peak here is the same height as these other 2 peaks. And so then I've got a 3s2, and then after that I know I'm going to go to the 3p, and then if we look at this one, this particular spectra has these nice little dashes over here to help you with the relative heights. But we can also look at this and go, well, this is not the height of the 6, it's more than twice the height of the 2. If it was twice the height of the 2, it'd be 4. If it was the height of the 6, it'd be 6. Therefore, it must be 5. You can't have half an electron, so it has to be 5. If you also look over here, though, on the side, it's 1, 2, 3, 4, 5. It's the height of the 5th tick mark. So this would be 3p5. So our total electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5, which does actually match the electron configuration for chlorine, which it should, because that's what it is. So you can use this to determine the electron configuration. That's probably the most common use of PES for AP Chem. You might also be asked to draw in or sketch over an existing chart to show, or an existing spectra to show what an ion might look like, or how it would shift if there's an additional energy level or things like that. So you should have a general understanding of what direction things should go. But in general, you're most often going to be using these to come up with an electron configuration to then you can use that to identify the atom or the type of element. And so the key here is to know that higher energy means lower energy levels, so the ones closer to the nucleus. So you'll want to watch your x-axis to figure out which side that is going to be. And that is how we use photoelectron spectroscopy.